In this video, we're going to explore Green's theorem. We're going to apply the circulation form of Green's theorem. We're going to apply the flux form of Green's theorem. We're going to calculate circulation and flux on more general regions, and we're going to love Green's theorem because it's going to make life a little bit easier. So if we recall from Calculus 1, we have this integration from a to b of f prime of x dx can be evaluated as the antiderivative of f evaluated at b minus the antiderivative of f evaluated at a, which basically says the integration or the integral over the region but below the graph of f prime of x and above the line segment from a to b depends only on the values of f at the endpoints a and b of that line segment. Since a and b are the boundary of the line segment AB, we can calculate the integral of f, the integral from a to b, of f prime of x dx based on the information about the boundary of the line segment a to b. This same thing is true when we are looking at the fundamental theorem of line integrals. Now remember from the last section, these were lovely. Green's theorem. Well, what is Green's theorem? I'll explain what it is, but let's talk about why we want it. So first of all, what Green's theorem allows us to do is to calculate double integrals over the region D based solely on the information about the boundary of D. We can also calculate the line integral over a simple closed curve C based solely on the information about the region that C encloses. And it connects a double integral over a region D to a line integral about the boundary of D. Well, that sounds nice. So what is this all about? Well, let D be an open, simply connected region with a boundary curve C that is piecewise smooth, simply closed curve orientated counterclockwise. Let F be the vector field described by P, Q, with component functions that have a continuous partial derivatives on D. If this is all true, then the circulation over the curve C of f dotted with dr will be equal to the circulation over the curve C of p dx plus q dy, which is equal to, and this is the nice part, the double integral over the region D, where I have q with the derivative, the partial derivative of q with respect to x, minus the partial derivative of p with respect to y dA. So here is an example of my curve C. Here is my curve C. My region is this shaded region D, and I'm going over this vector field you can see in the background. Green's theorem can be used for only two-dimensional vectors. Field F, if F is a three-dimensional vector field, then Green's theorem does not apply. That's okay. Don't panic. We'll have something nice. Since the integration over the curve C of p dx plus q dy is equal to the integration over the curve C of f dotted with t ds, this Green's theorem version is sometimes referred to as the tangential form of Green's theorem. If we're asked to evaluate the line integral by applying Green's theorem over this curve C of 2xy dx plus xy dy, where C is a path from 0, 0 to 1, 1, along this y is equal to x cubed, and from 1, 1 to 0, 0, from the graph y is equal to x, orientated counterclockwise direction. So what exactly is going on? Well, let me just draw a quick little sketch. I'm actually going to zoom in on here so I can have lots of space. I'm just going to draw a quick little sketch. So we're going to start at 0, 0. We're going to end at 1, 1, and we're going to go along the curve y equals x cubed. So this is the curve y is equal to x cubed. I start here at 0, 0, and I end right here at 1, 1. Then I'm going to go from 1, 1 to 0, 0, and I'm going to go along this curve, which is y is equal to x. So this is y is equal to x. So we know by Green's theorem that the circulation along the curve C of 2xy dx plus x plus y dy can be evaluated as the double integral over the region D of the partial derivative of my 2xy with respect to x, or excuse me, my partial derivative of x plus y, so x plus y, minus my partial derivative with respect to y of my 2xy dA. Now notice I'm not going to decide who I'm going to integrate with first. I'm not going to make that decision yet. So then this integration over the region D is going to be, well, the integral of xy with respect to x is 1 minus the integral of 2xy with respect to y is 2x. And then I'm just going to have a dA. Now I've got to decide who I want to integrate with respect to first. And I think I'm going to integrate with respect to y first. And y is going to be bounded from below by the x cubed and above by the x. So this is going to be equal to the integration. I'm going to be bounded from below by x cubed. I'm going to be bounded from above by x. And the reason I'm choosing with respect to y first is because this is in terms of x. That's the only reason. And then my x, as you can see from my picture, is going to go from 0 to 1. So my x is going to go from 0 to 1. So from 0 to 1. And so I'm going to have 1 minus 2x. I'm going to do it with respect to y first and then x. And this is going to be a really lovely integration. It's going to go from 0 to 1 of 1 minus 2x. And then I'm going to have y evaluated from x cubed to x dx. So this is going to be from 0 to 1 of 1 minus 2x. And I'm going to have x minus x cubed dx. I would multiply this thing first, so from 0 to 1. And when I multiply this, I'm going to get 2x to the 4th minus x to the 3rd minus 2x squared plus x dx. And this then becomes, after I do the evaluation, my final answer is negative 1 over 60. Isn't that nice? So let's take a look at my next example. I have the curve. Integrate over the curve of sine x cosine y dx plus xy plus cosine x sine y dy, where c is the boundary of the region. C is the boundary of the region lying between the graphs y is equal to x and y is equal to the square root of x orientated counterclockwise direction. Okay, so once again, I'm just going to draw this. So I have my first curve. This is my curve. Y is equal to, oh, actually, that's not my first curve. My first curve is going to be y is equal to the square root of x. And then my second curve is going to be y is equal to x. So we're going in counterclockwise, and you can see that I'm going to start at 0 and end at 1, and then go from 1 to back to 0, 0. So from 0, 0 to 1, 1, and from 1, 1 back to 0, 0, because I'm going to go counterclockwise. So I would start along this curve and then come back because I'm going counterclockwise. So using Green's theorem, the integration along the curve C of the sine of x, the cosine of y dx, plus the xy plus the cosine of x sine y dy can be rewrote as the integration across the region D of d dx of xy plus the sine of y, the cosine of x, minus the partial with respect to y of the sine of x, the cosine of y, dA. Again, I'm not going to make the decision on which way I am going to do this integration, so I'm just going to leave it with the region D, and I'll make a decision in a moment. So let's do our partials now. I'm going to have y plus the sine of y. Oop, it's going to be a negative So I need to change this to a minus. So minus the sine of x. And then it's going to be minus, and I'm going to do the derivative of the sine of cosine y, so it'll be a plus the sine of x, the sine of y, dA. I'm just going to take this parenthesis off, and you can see that my sines end up canceling each other out, which is actually really quite lovely. So this is going to be integration over the region D of y dA. So I think since I have a y here, I think I'm going to integrate with respect to x first. So I'm going to integrate with respect to x first. My y is going to go from 0 to 1. So my y is going to go from 0 to 1. My x is going to be bounded below, which will be this one, and bounded above by this one. So below, which is the curve y equals x squared, I'm going to solve for x, so I get y squared, and bounded above by the line. So I end up with that, and then I have y dx dy. So I get from 0 to 1 of yx evaluated from y squared to y dy, which gives me from 0 to 1 of y minus y squared dy, which is from 0 to 1 of y squared minus y cubed dy, which gives me 1/3 y cubed minus 1/4 y to the 4th power, evaluated from 0 to 1, which gives me 1/3 minus 1/4, same common denominator, I get 1/12, and there's my final answer. Okay, let C be a curve consisting of the line segments of 0, 0 to 1, 1 to 0, 1, and then back to 0, 0. Find the value of the curve. So I'm just going to draw this. Line segment starts here, so this is starting at A, and then I go to 1, 1, so I'm going to go here, I'm going to call this B, just so I can keep track of where I'm going. And then I'm going to go to 0, 1, so I'm going to go to this point C, so this is 0, this is C. And then so I'm going to go in this direction, and then in this direction, and then back to 0, 0. Find the value of this, and it's counterclockwise, that's kind of important, of C, of the integral along the line, along the curve C of x, y dx, the square root of y squared plus 1 dy. So we know that this is really a circulation. This is really a circulation because we're the way that we are orientated and the way that we close itself. So by Green's theorem, this is going to be equal to over the double integral over the region D of the partial with respect to x of the square root of y squared plus 1. We like that one. Minus the partial with respect to y of xy dA. So this is going to be the region D, double integral of the region D over 0 minus x dA. And now we just have to figure out which way we want to go with our integration. Do we want to integrate with respect to x first or with respect to y first? And since this is the same thing as the negative double integral over the region D of x dA, I think I'm going to integrate with respect to y first. So to figure out how y is being bound, well, y is being bound below by this line, which is the line y equals x, and it's bounded above by 1. So it's going to go from x to 1. And then my x is going to go from 0 to 1, and don't forget the negative out front, of x dy dx, which is going to be negative from 0 to 1 of my integration, so xy evaluated from x to 1 of dx, which is negative from 0 to 1 of, well, it's just going to be x1 minus x dx, which is the negative from 0 to 1 of x minus x squared dx, which now integrates really nicely into x squared divided by 2 minus x cubed divided by 3. Don't forget the negative out front, from 0 to 1. So I get negative 1/2 plus 1/3. Ooh, we always like these. Common denominator of 6, so I'm going to have negative 3 minus 2, so negative 1/6. Let's take a look at the next example. We want to find the area of the region enclosed by the parametric equation, where I've got p of theta is equal to cosine theta minus cosine squared theta I plus sine theta minus cosine theta sine theta j for theta running between 0 and 2 pi. Now, what we're really doing is we're really looking at the fact that we can consider this going in the counterclockwise direction. So we can consider it going in the counterclockwise direction, and you can confirm that's exactly the way it's moving. Now, there's a little nuance in the book. I believe it's, let me see, it's after example 6.4 in the book. It's this little nuance that says, hey, the area of the region D, let me write it this way, area of the region D can be wrote as the double integral over D, dA, which, little knockdown from Green's theorem, is 1/2 the circulation over the curve C of negative y dx plus x dy. So what we want to do then is we want to figure out what is x dy, and we want to figure out what negative y dx is. Well, x of t must be equal to this because it's in the x position. That's going to be equal to the cosine of theta minus the cosine squared of theta. So then x prime of t must be equal to the cosine of theta plus 2 the cosine of theta, the sine of theta. Similarly, y of t must be equal to this, so it's in the y position, so the sine of theta minus the cosine of theta, the sine of theta, so then y prime of t, the cosine of theta, and then by the product rule, I'll do the derivative of cosine first, which is negative sine, so that becomes plus the sine of theta times sine theta, so sine squared of theta. Then with the derivative of sine, which is cosine, multiplied by the negative, so negative cosine squared of theta. But if I pull out a negative out of there, that becomes a double angle. Don't necessarily need to do that, but I do, because I'm going to have to multiply stuff here in a minute. I want to have the least number of terms as possible. So I'm going to write this as the cosine theta minus the cosine 2 theta. Okay, so the first thing I'm going to do now is find my x dy. So I'm going to find my x dy. So x dy is going to equal to this x, which is the cosine of theta, minus the cosine squared of theta, multiplied by the y prime, which is this, the cosine of theta minus the cosine of 2 theta. Now, when I multiply this baby, and I'm not going to force you to watch me do that, multiply it through, use the appropriate trig identities when it's necessary. I'm going to get 1/2 the sine of 2 theta, cosine of theta, minus 1/4 the sine of 4 theta. I'm going to do the same thing for the y dx, where this is y, so it'll be the sine of theta minus the cosine of theta, the sine of theta, multiplied by this y prime, which is the cosine of theta, plus 2 the cosine of theta, the sine of theta. And once again, I am not going to make you watch me go through all of that and figure out using all the trig identities to simplify it. What this is going to be equal to is -1 plus 1/2 the cosine of 2 theta plus 1/2 the cosine of 4 theta plus 1/2 the sine of 2 theta and then the sine of theta. Now, this is lovely. We can go back up to here and said, well, this is equal to 1/2 of this. So we have the 1/2, the circulation over the curve C, of -y, so this would become 1 minus 1/2 the cosine of 2 theta minus 1/2 the cosine of 4 theta. Keep moving on, minus 1/2 the sine of 2 theta. That is my -y dx. And then plus, I have 1/2 the sine of 2 theta cosine theta minus 1/4 the sine of 4 theta. Well, that's lovely, isn't it? D theta. Bam. D theta. Now, this actually isn't all that bad. It's not delicious, but it's not all that bad. We do get some cancellations. And we do get some simplifications. So this ends up becoming, this is equal to, someday my pen will be a part of the conversation. This is going to be equal to 1/2. Now, because my shape is going from 0 to 2 pi, it's going to be the integral from 0 to 2 pi of -1/4, after some simplification, the sine of 4 theta plus 1 minus 1/2 the cosine of 2 theta minus 1/2 the cosine of 4 theta d theta, and then plus my second half, which is 1/2 the integral of 0 to 2 pi of the cosine squared theta, the sine of theta, d theta. All I'm doing is just breaking it up into the easier integrations. And then plus 1/2 from 0 to 2 pi of the cosine theta, the sine squared theta, d theta. You don't necessarily have to do this. I just want to say you don't necessarily have to do this. It just is, it's kind of nice to be able to see the integrations a little bit easier. And then, of course, you let u equal here the cosine theta. Here you would let u equal the sine theta, the normal u sub. And then these are really just nice, straightforward integrations. And I end up with, when I'm totally done doing my integrations, I end up with pi. That's a lot of work for pi, but there it is. Let's take a look at this next example. Use Green's theorem to calculate the work done by the force F on a particle that is moving counterclockwise along a closed path C, where F is equal to xy, the vector F xy is equal to xy in the I direction, x plus y in the j direction, and the path is x squared plus y squared is equal to 4. So I'm just going to draw a quick little sketch of the path, and you're like, oh, it's a circle with a radius of 2, and that would be correct, and we're going counterclockwise. Do you like my circle? It's like the best circle you have ever seen in your entire life, said no one. So what we're really asked to do is to do the integration along this curve, the circulation actually, of the vector F dotted with a dr, which is equivalent to the circulation across the curve C of the vector x, y comma x plus y, dotted with a dx comma dy, which is the circulation across the curve C of xy dx plus x plus y dy, which, by Green's theorem, is the double integral over the region D of the partial derivative with respect to x of x plus y minus the partial derivative with respect to y of xy dA. Again, I'm not going to choose what I'm going to do with respect to first, which is equal to the integration from, I'm not going to choose, I'm going to go from just the integration of d. I have, when I do my partials, I have 1 minus y dA. Now, this clearly is going to be polar at this point because this is what I'm integrating over, right? So I'm integrating over the circle, so polar is my best friend. Using polar, we know we have these replacements. Y is equal to r sine theta. We know that x squared plus y squared is equal to r squared. So then my r is going to run between 0 and 2. And my theta, because I'm doing a full circle, is going to run between 0 and 2 pi. So now I'm going to integrate, and it doesn't really matter which one I integrate with respect to first. I can do r, I can do theta. I think r might be the easier one to integrate from first. So I'm going to go from 0 to 2 pi on my theta, which I'll do last, from 0 to 2 on my r. I have 1 minus r sine theta dr d theta. So then with respect to r first, I'm going to go from 0 to 2 pi of r minus r divided by 2, the quantity squared of sine theta, evaluated from 0 to 2 of d theta. And when I get totally done, my final answer is a nice, lovely 4 pi, which is really, really kind of nice. Take a look at this application. David and Sandra are skating on a frictionless pond in the wind. Why do we care about all this? Well, frictionless means that we don't have to worry about the coefficient of friction, and the wind tells me I have a vector field. David skates on the inside along a circle with radius 2 in a counterclockwise direction. Lovely. Sandra skates once around the circle of radius 3, also in a counterclockwise direction. Lovely. The wind at the point xy, 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 I think that's probably a typo, is the vector field of xy is equal to x squared y plus 10y I, and 3, or x to the third, plus 2xy squared in the j direction. Use Green's theorem to determine who does more work. So we have, I'll draw a quick little picture. We have, here's David, and here is Sandra. And I'm going to do the circulation of the curve C of F dotted with dr. These are both vectors. And this is going to be equal to the circulation along the curve C of the vector x squared y plus 10y, comma, x cubed plus 2xy squared dx dy, dot product here, which is going to give me the circulation across the curve C of x squared y plus 10y with the dy, and then it's going to be, or excuse me, dx, and then it's going to be plus x cubed plus 2xy squared dy. Now, because of Green's theorem, we're going to have the double integration over the region D of my partial with respect to x of x cubed plus 2xy squared minus the partial with respect to y of x squared y plus 10y which gives me the double integration over the region D of, I'm going to have 3x squared plus, let me see, 4, so it'll be 2y squared minus, and then with respect to y, I'm going to have x squared, and then minus 10. dA, don't forget the dA. And so this will be the double integral over the region D of, I'm going to end up with 2 x squared plus y squared, and then minus 10. Now, why am I doing that? Well, if you're thinking, probably want to go into polar, you are correct. So we're going to start with David. We're going to do David's in blue. Here's David. David's in blue, just like before. I'm going to go from 0 to 2 pi. I'm going to go from 0 to 2, because that's his radius, of 2r squared minus 10 dr d theta. And I end up with David's, I'm going to get a negative 24 pi, whatever my work units are, work units. Now, I'm going to do Sandra's, so I'm going to go from 0 to 2 pi of 0 to 3 of 2r squared minus 10 dr d theta. And when I do Sandra's, I'm going to get negative 9 pi work units. So even though Sandra is going in a bigger circle, you would think she was doing more work, but the wind is really going to help her on parts of her big circle. So David actually is doing more work. All right, now let's look at the flux form of Green's theorem. Let D be an open, simply connected region with a boundary curve C that is a piecewise smooth, simple closed curve that is orientated counterclockwise, be a vector field with component functions that have continuous partial derivatives in an open region containing D. Then, the circulation over the curve C of F dotted within ds is equal to the doubled integration over the region D of P with respect to X plus Q with respect to Y of dA. Here's an example visually of what's going on. Let me just lock the screen in here again. So you can see here is my region D. Here's my normal vectors. Here's my curve C. Here's my vector field. I am going counterclockwise. Now, all of these statements are equivalent ways of defining a free source field F of PQ on a simply connected domain. Note the similarities between the properties of a conservative vector field and this one. The flux, which is the circulation over the curve C of F dotted within ds across a closed curve C is 0. C1 and C2 are curves in the domain of F with the same starting points and ending points. Then the integration of C1 of F dotted with ds is equal to the integration of C over C2, F dotted with ds. So in other words, the flux is independent of path. There's something called a stream function G of xy for F. A stream function F is equal to PQ is a function G such that P is equal to G, P will be equal to the function G with its partial with respect to Y, and Q is going to be equal to the negative G with a partial with respect to X. Geometrically, F is equal to AB is tangential to the level curve at G of G at AB. Since the gradient of G must be perpendicular to the level curve G at AB, the stream function G has a property of the vector, or the function, the antiderivative of the function AB dotted with a gradient of G at AB must be equal to 0 for any point AB on the domain of G. Stream functions play the same role for source-free fields that potential functions play for conservative fields. Now, if you remember from last time, we had conservative fields. Now we have not necessarily conservative fields. And the partial with respect to P plus the partial with respect to Y, or Q with respect to Y, is equal to 0. So we're going to calculate the outward flux F of F, which is equal to negative x in the I plus 2y in the j over a square with corners at negative 1, 1, 1, 1. So let's draw a quick little picture. So here, 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 and here. Here's y, here's x. This is 1, 1, negative 1, negative 1. We're going counterclockwise, so we're going in this direction. So the flux along the curve C is of F dotted with N ds has to be equal to the double derivative over the region D of the partial with respect, the partial P with respect to x plus the partial of Q with respect to y, dA, which is going to be equal to the double integral over the region D of d of dx of negative x plus the partial with respect to y of 2y dA, which is going to be the double integral over the region D of negative 1 plus 2 dA, which is going to be the double integral over the region D of dA, which is just a, which from here to here is 2. From here to here is a distance of 2, so it's 2 multiplied by 2, so the answer is just 4. It's kind of nice. Okay, let's take a look at this example. Let f, the vector f, be defined as y squared minus x squared in the I, x squared plus y squared in the j. Let C be a triangle bounded by y equals 0, x is equal to 3, and x is equal to y. So again, I'm going to draw a quick little picture. And I have x is equal to 3. I have y is equal to 0. And I have y is equal to x. And we're going counterclockwise, so we're going in this direction. Find the outward flux of F through C. So the flux over the curve C of F dotted with N ds is going to be equal to the double integral over the region D of P with respect to x plus Q with respect to y dA, which is equal to the double integral over the region D of my partial with respect to x of y squared minus x squared, and then plus my partial with respect to y of x squared plus y squared dA, which is going to be the double integral over the region D. And again, I'm going to wait to see which one I'm going to integrate with respect to first. I end up with x minus y dA. Now, I don't really have like one better than the other. So let's go ahead and integrate with respect to y first. So then x is going to go from 0 to 3. And then y is going to be bounded below by 0. And it's going to be bounded above by the line y equals x. So it's going to be bounded below by 0. And it's going to be bounded above by x of x minus y dy dx. This, when I integrate it, and I'm tired and you're bored, so I'm just going to tell you the answer is negative 9. Let's take a look at the next part of this, which is the Green's theorem over general regions. With general regions, we may have holes in it. Up until now, we couldn't handle holes, but now we're going to extend Green's theorem so that we can have a finite many number of holes within our region. So we're going to let D be a region And let C being a component of the boundary of D, we say that C is positively orientated if we walk along C in the direction of orientation. The region D is always on our left. So now we can't just talk about clockwise. We have to say, where is this region? The region is on our left. Therefore, the counterclockwise orientation is the boundary of a disk that is a positive orientation. The curve C is negatively orientated if we walk along C in the direction of the orientation, and the region D is always to our right. The counterclockwise or the clockwise orientation of the boundary of a disk is a negative orientation. We didn't talk about that now we are. We're going to let D be a region with finite many holes so that D is finitely many boundary curves, and denote the boundary D by the partial D. See this below. To extend Green's theorem so it can handle this region D now, we're going to divide up D into two regions, D1 and D2, in such a way that this region D is going to be equal to this region D1 and this region D2, because we want to address those holes in there. So if we assume the boundary of D is orientated like we did, with the inner holes given a negative orientation, the outer boundary given a positive orientation, we're going to end up with this. So if F is a vector field defined by D, then Green's theorem says that the circulation, the partial region D of F dotted with a dr is going to be the circulation of the partial of D1, F dotted with dr, plus the circulation of the partial of D2, F dotted with dr, which ends up, when I get totally done, with the integral, or the double integral over the region D of Q with respect to X minus P with respect to Y of dA, which means Green's theorem holds for holes. And with the same kind of logic, we now have a Green's theorem for flux over a general region. So evaluate the circulation over the region C, over the curve C, where I've got y cubed dx minus y, or x squared dy, where C includes two circles of radius 1 and radius 2, centered at the origin, both with positive orientation. All right. So the first thing we're going to do is we are going to set up our circulation over the curve C of y cubed dx minus x cubed dy. This is going to be equal to the double integral over the region D of my partial with respect to x of negative x cubed minus my partial with respect to y of y cubed dA. This is just Green's theorem. And then this is going to be over the region D of negative 3, and I have x squared plus y squared and dA. Just kind of made that a little bit easier. So then this is going to be equal to negative 3 over the region D. I'm going to have this as r squared dA because I'm going to use polar. So this is going to be equal to negative 3 integrated from 0 to 2 pi of, and then r first from 1 to 3 because of my radius of 1 and radius of 3, of r squared r dr d theta. So when I get totally done integrating, I get a negative 120 pi, and that is my final answer. And that is my final example in this video. Thanks for watching all 44 minutes and 10 seconds, 11 seconds, 12, 13. Anyways, I'm tired. You're tired. We'll see you in class.